Good morning, everybody. I'm going to give people a minute or two to check in before I start. I guess I should put a recap on. Good morning, everybody.
Morning.
Another beautiful Tuesday. Let's see. Yeah, manage participants. Mute all. Mute themselves. Yes. Okay, a couple things while people are still tuning in. Let me share. Oh, hold on. Oop. Online resources. So share screen. All right, a couple things as people are tuning in. One, I have to apologize. The lecture that I gave yesterday, and I covered a lot of great stuff. For some reason, the Zoom lecture didn't record. Spent like an hour and a half trying to figure it out. I uploaded everything to Zoom's tech support. Hopefully, they're going to be able to convert it. But since it didn't convert, I did another about 20-minute lecture where I just basically recapped everything I talked about in the Zoom lecture. So, and the other thing is, a couple things, I posted labs for Wednesday. So this is sort of a second part. It's kind of like conservation of energy part 2. I called it modified Atwood's machine because it's the system that we're looking at. And was there anything else? That was it. Oh, and just in terms of a preview for the schedule. So this week, Tuesday, PLC number 10 is due. You already have all the information you need to do it. Wednesday, lab number 8 is due. That was last week's lab. I decided to just have people turn in a lab the next week rather than waiting 2 weeks to turn in 2 labs at the same time. Thursday, chapter 10 homework, and then Friday, chapter 10 quiz, and then a little preview. Next Wednesday is going to be our celebration number 2. It's going to cover chapters 8, 9, 10, and 11. Chapter 11 homework I'm not going to collect, but I'll talk a little bit more about the celebration. I'll probably make a video on Friday. So it's probably going to be like the quizzes, only a longer quiz. My first thought is I'm going to have probably 20 multiple choice questions. I'll give you 2 hours for the celebration. It'll sort of be like the quizzes, it's just a longer version. Okay, so I will record a video probably on Friday giving you some information about the upcoming celebration. So let's go a little bit about, let me just sort of recap the recap. So let me get that a little bit bigger. This equation here, let me draw, let's use red. So this is our one giant equation that's basically all of chapter 10. And it says the following: the work done by all external forces on a system. And remember, you get to define the system. Anything that's not the system is the environment. Any force the environment exerts on the system is an external force. So this left-hand side is the work done by all external forces. I'll get to that in a second. That can change the total energy of the system, and we're considering 4 forms of energy. Energy of motion called kinetic energy, 1/2 mv squared. Gravitational potential energy, mgy. Elastic potential energy, 1/2 k delta x squared, and the change in thermal energy. So all of these delta terms, you know, are final value minus initial value. So if I take all of my initial values and put them on one side, all of my final values and put them on the other side, the second form of the equation, and this is sort of the one that I like to start with, is my initial kinetic energy plus my initial gravitational potential plus my initial elastic potential plus the work done by external forces, they are doing stuff out front, equals final kinetic plus final gravitational potential plus final elastic potential plus the change in thermal energy. So one thing let me mention, we generally do not know what the initial thermal energy is and what the final thermal energy is. But we know how much thermal energy increases because of friction. That equation is the force of kinetic friction times delta x. So this third equation is really just the second equation where I have specifically written out all of the energy terms. So kinetic energy is 1/2 mv squared, elastic potential energy is 1/2 k delta x squared, gravitational potential energy mgy, and so on and so forth. 4 important things to consider. 1, when you're dealing with gravitational potential energy, you get to define y equals 0 anywhere. In general, it makes sense to define it either where it starts at or where it finishes at. Potential energy is always an interaction between 2 objects, 2 or more objects. So I can't have potential energy unless I have a system of at least 2 objects. If I'm going to use gravitational potential energy, Earth has to be part of the system. If I'm going to use elastic potential energy, the spring has to be part of the system. And if I'm going to include thermal energy, all objects whose temperature changes has to be part of the system. All right, let me just real quickly check out these comments. Meeting controls. All right, let me stop this for a second. I keep crashing. Sorry about that. Somebody rose a hand. Christopher, do you have a quick question?
Yeah. It was just, I was wondering like how we were going to take the celebration exactly. Like, is it going to just be like
It'll be just
online?
like the quiz. Basically, it'll be due Wednesday by midnight. I will give you 2 hours. The PLC that's going to be due next week is basically just going to be you creating a cheat sheet. Even though the quiz, or even though the celebration, like the quizzes are going to be completely open notes and everything, much easier if you have everything organized on one sheet. So the PLC for next week will just be creating your cheat sheet. And my thought is that you'll have 2 hours to do the 20 multiple choice questions due by Wednesday at 11:59 p.m. Okay. But again, I will make a detailed video of that on Friday, probably.
All right.
Okay.
That's next Wednesday?
Next Wednesday.
Okay.
Okay, so going back to, what do I do? April 14th. So let me just recap this one more time, and then let's just do example problems and clicker questions. So the big equation is the work done by all external forces equals the change in energy of the system, which equals the change in kinetic energy, plus the change in gravitational potential, plus the change in elastic potential, your book's using SP, change in elastic or spring potential energy, and the change in thermal energy. If I take all the initial values and all the final values and put them to one side, this equation is really the work done by all external forces, plus the initial kinetic energy, plus the initial gravitational potential, plus the initial elastic potential, equals the final kinetic energy, plus the final gravitational potential, plus the final elastic potential, plus any change in thermal energy. And then last but not, so this personally is how I like to start all the problems. And then each one of these, I could write them out. My initial kinetic energy is 1/2 mv initial squared. My initial gravitational potential energy is mgy initial. My initial elastic potential energy, delta kx initial squared, equals my final kinetic plus my final gravitational potential plus my final elastic potential plus my change in thermal energy. So this is really chapter 10 in a nutshell, keeping in mind that I have to include the Earth as part of my system if I'm using gravitational potential energy, have to include the spring as part of my system if we're using elastic potential energy. Work done by all external forces is what this is indicating, and most of our forces are going to be constant. So for the work, we can use the force dotted into the displacement. 2 other things. One, anytime you hear of conservation of energy, that's basically if the work done by all external forces is 0. And if that's the case, we say the system is isolated. And I mentioned, I think that's a weird word. To me, an isolated system is one that's not being acted on at all. But in physics, an isolated system is one in which the total work done by all external forces is zero, so no energy is being added or removed for the system. If this is the case, then the change in energy of the system is equal to zero. That's in essence what conservation of energy says, is the total energy of the system doesn't change because there's no work being done by outside forces. And then often you'll hear of conservation of mechanical energy. So mechanical energy is just defined as the kinetic energy. Let me try that one more time. Mechanical energy, you guys may remember from high school physics, is just defined as the kinetic energy plus all forms of potential energy, which right now is just elastic potential energy and gravitational potential energy. So if the work done by external forces is zero and there's no friction, which basically means that there's not going to be any thermal energy, then what I can say is my initial kinetic energy plus my initial gravitational potential plus my initial elastic potential equals my final kinetic plus my final gravitational potential plus my final elastic potential. Woo! Okay, let's do a clicker question and then do some example problems. And pretty much is just working with these equations right here. So, clicker question. Let's take first a look at clicker question 10.4. So, question is the block's mechanical energy, and that's just the sum of kinetic plus potential, is it increasing, decreasing, or constant in the region AB, BC, and CD? And this whole region here, AB, BC, is supposed to be ice, so there's no friction. This region CD, there is some friction. So the question is mechanical energy increasing, decreasing, or constant in region AB, BC, and CD? Take 10 seconds, think about that. What do you think? So in this case, the answer is constant, constant, decreasing, D. If there's no frictional forces, then there's going to be no thermal energy being generated. And in this case, if I consider my system, let's say to be, what is this? The block and the earth. Are there any external forces acting on the system? Yes, the normal force. But the normal force is not doing any work, so it's not adding or removing energy from the system. So what's happening as it goes from A to B is gravitational potential energy is decreasing, but kinetic energy is increasing. However much potential energy it loses, that's how much kinetic energy it gains. It's going the fastest at B. And then going from B to C, now the potential energy is increasing, but kinetic energy is decreasing. So the total energy from A to B and from B to C doesn't change. But now from C to D, there's frictional forces. Friction is going to cause heat to be generated, so I'm going to have thermal energy increasing. And if I wanted to know how much it increased, I would need to know the force of kinetic friction and the displacement. But friction is removing energy from the system, and so mechanical energy is not conserved. Why can't I pull up chat here? If it was all energy, including thermal, would it be constant or is it still decreasing? Great question. So mechanical energy is just kinetic plus potential. If they asked, is the total energy of the system constant, changing, or constant, decreasing, or increasing? If I just said the total energy, that would be constant the entire time. From region C to D, some of the energy is getting converted into thermal energy, but the total energy isn't changing if there's no work being done by outside forces. Okay, let's do a couple example problems.
Hey, Joe.
Yes.
Why was the normal force an external force in the last question?
It's funny, I just forgot the last question. What is it doing? Oh, clicker question. I define my system as just the block and the earth. And so the normal force is basically the surface exerting a force on the block. So if the normal force were to be if the normal force were to be an internal force, I would need to include the surface as part of my system.
Yeah. Okay.
And in fact, now that I say that, I realize I made a mistake. I cannot include thermal energy unless I'm including all objects that heat up as part of the system. So actually what's happening here, if I'm not including the surface as part of my system, is in this region right here, friction is doing negative work, which is decreasing the overall energy of the system. Now, if I included my surface as part of the system, then I could include thermal energy. And like Laura had asked, the total energy, if I include as my system the earth, the block, and the surface, is not going to change. I'm going to have thermal energy being generated, but the total amount of energy doesn't change unless an outside force does work on the system. Christopher, quick question.
Yeah, so what about like heat getting transferred to the, like,
I think you just cut out. Okay, Christopher, I'm going to come back to you. I'm going to do an example problem. Okay, what's a good one to do? Let's
counted in your system?
Okay, all right, off with the recap. So let's take a look at problem 1020. Draw. It says a 15,000 kilogram jet plane lands on an aircraft carrier. Its tail hook snags a cable to slow it down. Cable is attached to a spring with spring constant 6,000 newtons per meter. If the spring stretches 30 meters to stop the plane, what was the plane's landing speed? So this was problem 1020. Is that right? 1020. And we were told, just to give our gibbons, just for me to be specific, is the spring constant of the spring is 60,000 newtons per meter. One, what does this mean? It means this is a really, really stiff spring. It would take 60,000 newtons of force to stretch this spring by 1 meter. We were told the spring stretches, going to call this delta X final, of 30 meters. And the mass of the plane was 15,000 kilograms. And what I want to know was, what is the initial speed of the plane before it got snagged by the spring? So one, let me try and draw this setup. And I apologize for the lame drawing. I'm trying to draw this from the book. So here is a plane. It's one of these new square planes they just came out with. It's traveling at some initial speed right when it hooks the spring. So let's just say here's the spring and it's attached to, I don't know, something like this. So I've got a plane which is moving to the right at some speed. It just hooks the spring. Right now, this is where the spring is not stretched or compressed. Then the spring travels the box stretches the spring a total distance of 30 meters in slowing it down. So this spring has now been stretched a total distance of 30 meters. It ends up at rest, and what we want to know is, what was the initial speed that it started with? That's not a question mark here. So, plane moving at some initial speed. It hooks onto a hook. This hooks onto a spring. Spring has a spring constant of 60,000 newtons per meter. The spring stretches 30 meters as the plane goes from some initial speed to some final speed of 0. And you want to know what was the initial speed of the plane. So whenever you're doing these, you want to define your system. So in this case, I'm going to define my system as the plane, the Earth, and the spring. If that's the case, if I were to draw a free body diagram of the forces acting on the plane as the spring is slowing it down, I basically have the normal force on the plane. I've got the force of gravity, mg, and I've got the spring exerting a force slowing it down. So if my system is the plane, the Earth, and the spring, the only external force is now the normal force. So my external forces are just the normal force. And anytime the force is perpendicular to displacement, that force is not doing any work. So in this case, the plane is moving to the right, the normal force is straight up, the work done by gravity is 0. So our big equation is the work done by all external forces plus my initial kinetic energy plus my initial gravitational potential energy plus my initial elastic potential energy equals my final kinetic energy plus my final gravitational potential plus my final elastic potential plus any change in thermal energy. So how I would do every energy problem is start off by defining your system. Then write down the big equation, which is the one I just wrote down. And actually, even before that, if I'm going to include gravitational potential energy, I want to define where my y equals 0 is. And in this case, the plane is not changing in elevation. I'm just going to define my y equals 0 to be the height that the plane has once it hits the aircraft carrier, whatever the hell it's landing on. So if I define y equals 0 at the elevation the plane has, question for you is, here are 8 different terms for work in the various forms of energy. Quick question for you. How many of those 8 terms are 0? Take about a minute, think about that. Let me draw this in a different color. What do you think? I've got the work done by external forces. I've got initial kinetic energy, initial gravitational potential, initial elastic potential, final kinetic, final gravitational potential, final elastic potential, change in thermal energy. What do you think in terms of these 8 different quantities? How many of those are 0? What do you think? We'll go through this in 30 seconds. And time. So, work done by external forces. The normal force is the only external force. It's not doing any work. So this term is 0. Initial kinetic energy, it is moving right as the spring attaches to it. That's not a 0 term. Final and initial gravitational potential energy. Since I defined y equals 0 at the elevation it is, no potential energy initially, no gravitational potential energy to end with. Now, what if instead I decided to define this not as y equals 0, but y equals 10 meters? Would that affect anything? And the answer is it never depends on where you define y equals 0, because the only thing that matters is how much potential energy changes. So if I didn't define my so remember, gravitational potential energy, mgy. If I didn't define y equals 0 to be at the elevation it is, but I defined that to be y equals 10 meters, then I would just have this same mgy term on both sides, and then I could just subtract it off. So in this case, it doesn't matter where you define y equals 0, because all that matters is how much the potential energy changes. Now, the spring, initially, our initial condition is when the spring just hooks onto the plane. It's not stretched or compressed at all. So my initial my initial elastic potential energy is 0. Now, what else do we have? Final kinetic energy. This ends at rest. So the final kinetic energy is 0. The spring is now stretched a distance of 30 meters. So this term survives. and there's no air resistance and no friction, so the change in thermal energy is 0. So what do I get? I basically get that the initial kinetic energy the plane has is equal to the final elastic potential energy in the spring. Or if I write this out in terms of the quantities, initial kinetic energy is 1/2 mv initial squared. My final elastic potential energy is 1/2 k times delta x final squared. I know the mass, I know k, I know how much the spring is stretched. I can solve for my initial speed. So what I'm going to get is my initial speed is the square root of k over m times delta x final squared. So what I get is the square root of, what was it, 60,000? 60,000 newtons per meter divided by 15,000 kilograms times 30 meters squared. And once you solve this, what you're going to get is, to two significant figures, 60 meters per second is how fast the plane must have been going if it got slowed down in 30 meters from a spring whose spring constant is 60,000 newtons per meter. So again, let me just recap one more time how we're doing these problems. So first off is, one, if it's a complicated situation, I draw a sketch. But you're always defining your system. And the reason that's important is because anything that's not your system is an external force acting on the system, which could change it. If I want gravitational potential energy, Earth is part of the system. If I want elastic potential energy, the spring has to be part of the system. Our big equation for chapter 10 is this one. Work done by external forces plus the initial energies equal the final energies plus any change in thermal energy. Then think about, are there any external forces doing work? If not, then I know the sum of the external force, sum of the work done is 0. And then I just have this equation and I'm just putting in things that are 0, solving for my unknown quantity. And again, you're always going to end up with an equation that, if I think about the energy, should make sense. So in this case, the plane was initially moving, it had kinetic energy, and then it came to rest, but it stretched the spring. So now the kinetic energy all got converted into elastic potential energy. Booyah! All right, let me pause. I'm lagging out. Questions I can answer on that specific example problem. All right, let's do a clicker question or two. Let me share the screen again. Let's go to this, and let's do a couple fun clicker questions. Fun? Yeah, they are fun. How fun? We'll see. Let's do a couple with springs. I can never get Jack. Super fun.
That was easy. That was easy. That was easy.
There we go. Super fun. Okay. Here, look at clicker question, whatever this is. Where's my little thingy? Draw. A box of mass m is pressed against but not attached to an ice steel spring of force constant k and negligible mass compressing the spring a distance x. So right now, this spring is compressed some distance x from its normal uncompressed lengths. We would be using delta x, but in this case, it's the same thing. After it's released, the box slides up a frictionless incline as shown in the figure and eventually stops. So we release this and the box is going to slide up to some final height. Where basically it stops and then it would start to slide back down. If we repeat this experiment with a box of mass 2m, which of the following are true? So now we're going to do the exact same experiment, compress the spring the same amount, but now the mass is twice as much. If that's the case, which of these 5 answers are correct? The lighter box will go twice as high up the incline as the heavier box. Just as it moves free from the spring, the lighter box will be moving twice as fast. Both boxes will have the same speed just as they move free of the spring. Both boxes will reach the same maximum height. Just as it moves free of the spring, the heavier box will have twice as much kinetic energy as the lighter box. What do you think? Take 10, 15 seconds, go through that. Really good question just to understand this conceptually. And let me just say a couple things while you're thinking about this. I would define for this problem my system as, what is this, a box plus the earth plus the spring. If we do that, again, the only external forces would be the normal force. But again, in this case, the work done by the normal force is 0, which means that the total energy is going to be conserved. So let's just look at that. If the work done by all forces is 0, what I can say is the initial, and 1, there's no friction. If there's no friction, then there's going to be no thermal energy generated. So if the work done by external forces is 0 and there's no friction, mechanical energy is conserved, the sum of kinetic plus potential. So what I have is my initial kinetic plus my initial gravitational potential plus my initial elastic potential equals my final kinetic plus my final gravitational potential plus my final elastic potential. So the question is, for this particular system, what is the energy transformation that's taking place? Well, 1, this is going to start from rest before I release it. And at the very highest point, it's at rest again. So my initial kinetic energy is 0. My final kinetic energy is 0. And again, I'm looking at my initial as when the box is still connected to the spring, and my final when the box is the highest point. My initial gravitational potential energy, if I define y equals 0 to be the elevation it starts at, it doesn't have any gravitational potential energy to start with, but the spring is compressed. It does have elastic potential energy. At the end, the spring is no longer stretched or compressed, but the mass is in an elevated position. So in essence, what I have is, initially the energy of the system is elastic potential energy stored in the spring. That all gets converted into gravitational potential energy. So what I have is 1/2 K times delta X initial squared equals mg y final. So if I have a mass that's twice as much, that doesn't affect the initial elastic potential energy stored in the spring. It's just 1/2 K times delta X squared. So the energy stored in the spring doesn't depend upon the mass you connect the spring to. But all of that elastic potential energy then all gets converted into gravitational potential energy, which means if I use something with twice the mass, it's only going to go half the height because gravitational potential energy depends upon mgy. And so if the mass is twice as much, my height can only be half as much. So the correct answer here is the lighter box will go twice as high up the incline as the heavier box. The heavier box has twice as much mass, and if it's going to end up with the same gravitational potential energy and it has twice the mass, it can only go half as high. Let's do one more along those same lines. Maybe this one a little bit faster. So this is a similar situation, except box of mass M is pressed against but not attached to an ideal spring of force constant K, negligible mass compressing the spring at distance X. Again, we're using delta X. After released, slides up the frictionless incline as shown and eventually stops. If we repeat this experiment but instead compress the spring twice as much. So now we're not using a mass that's twice as much. Now instead of compressing at X, we're compressing the spring twice as much. So same question, but now if I compress the spring twice as much, which of these answers are going to apply? Take a second and think about that. So one, going back, everything we did up here applies in terms of defining our system and the energies and things like that. So I'm still going to end up with, let me do this right here, my initial elastic potential energy is going to equal my final gravitational potential energy. And my initial elastic potential energy is 1/2 K times delta X squared. So here's the thing. Since elastic potential energy depends upon how much the spring is stretched or compressed squared, delta X squared, if I compress the spring twice as much, 2 squared is 4, that means the elastic potential energy increases by a factor of 4. So when I compress the spring twice as much as before, my elastic potential energy increases by 4 times. If that's the case, let's go through all of these and just look at them one by one. The box will go up the incline twice as high as before. No. If I have 4 times as much elastic potential energy, oh, I used elastic again here instead of spring. If I have 4 times as much elastic potential energy stored in the spring, and that all gets converted into gravitational potential energy, I have to go 4 times as high. Just as it moves free of the spring, the box will be traveling twice as fast as before. I'm going to come back to that one. C, just as it moves free of the spring, the box will be traveling 4 times as fast as before. Come back to that in a second. Just as it moves free of the spring, the box will have twice as much kinetic energy. Just before it released, the box has twice as much elastic potential energy. So one, we know that's not true. So I can look at this. One, I looked at this right when when the spring was still stretched or compressed, and then when the box has gotten to its highest point. Well, if instead, let's look at the box right when it leaves the spring, before it started to increase in elevation. If that's the case, then what happens is all of the elastic potential energy of the spring first gets converted into kinetic energy of the moving mass, and then that kinetic energy gets converted into gravitational potential energy. So now if I consider my initial condition to be when the spring is still stretched or compressed by a distance x or 2x, and my final condition to be when the mass is now no longer connected to the spring and moving, then what I would see is the initial elastic potential energy stored in the spring is going to equal the final kinetic energy of the block once the spring is done launching the block. Which means if this increases by a factor of 4 when I double the distance the spring is compressed, that means my kinetic energy has to increase by a factor of 4 too. Now, kinetic energy depends upon speed squared. So if I have 4 times as much kinetic energy, that means I must have been going twice as fast. So the box will have twice as much kinetic energy. No, just before it being released, the box had twice as much elastic potential energy. No, the box had 4 times as much elastic potential energy, which means the mass is going to have 4 times as much kinetic energy once the spring is no longer compressed. But 4 times as much kinetic energy actually means twice the speed. So the correct answer here was it's going to be moving twice as fast as it did before.
That was easy.
Okay, let's do another example problem. And let's see, what's a good one? Ooh, let's do 1048. Sam, whose mass is 75 kilograms, straps on his skis and starts down a 50-meter high, 20-degree frictionless slope. A strong headwind exerts a horizontal force of 200 newtons on him as he skis. Use work and energy to find Sam's speed at the bottom. So one, let me just sort of draw what I think is going on here, and then I'll do this on a different page. So we have, wow, that's horrible. We've got a 20-degree frictionless inclined plane. This person is starting from a height of 50 meters. And again, he's a box-shaped skier. And as they are sliding down, there is a headwind, which is 200 newtons, and it's acting horizontal. And what we want to know is what is his speed at the very bottom. So again, anytime you're doing this kind of problem, first think about how am I going to define my system? Then I think about what are external forces, are any of them doing work? So in this case, let's define our system as Sam plus the Earth. I'm defining the Earth as part of my system so I can use gravitational potential energy. If I didn't define the Earth as part of my system, then the Earth would be an external force doing work, and then I would need to look at the work done by gravity. But if I include the Earth as part of my system, now I can include gravitational potential energy. If I look at the forces acting on this skier, I've got the normal force, I've got gravity mg, and I've got this headwind, what should I call this? Horizontal force, let's just call this F. This is the headwind. Those are the only three forces acting. My system is the Earth plus Sam, which means that this headwind is an external force, this normal force is an external force. Well, as the skier goes down the incline, the normal force is perpendicular, which means the work done, well, one, let's just be specific. My external forces are the normal force and this headwind. Okay, so let me do this on a different sheet just so I can do the math. But the setup is I'm defining my system as Sam plus the Earth. I have two external forces, the normal force and this headwind. The normal force is not doing any work. So let's do more example problems. So this was problem 10.48. And let's go down. So again, just to be specific, here's where he starts. Here's where he ends. I'm going to define my y equals 0 at the bottom, which means my initial height is 50 meters. My final height is 0. They are starting from rest, Sam is, so his initial speed is 0. I want to know what is the final speed at the very bottom, and there is a headwind acting horizontally with a force of 200 newtons. So our big equation, the work done by all external forces plus the initial kinetic energy plus the initial gravitational potential energy. Now, there's no spring. And if it were me and there's no spring, I'm not even writing the elastic potential energy term. So if you don't want to do that, well, you're not really turning in the problems the way you were before. But yeah, I would start just looking at what are the forms of energy present. So this equals my final kinetic energy plus my final gravitational potential energy plus any change in thermal energy. So again, doing these problems, I define my system. That's important because anything that's not part of the system acting on the system is an external force, and I need to look at what is the work done by external forces. Then I have my big equation for work in all the different forms of energy, and then I'm really just plugging in what is 0 and then solving for the unknown quantity. So here, the work done by external forces, there is this headwind, which is doing work. I need to figure out the work done by the headwind. We will do that. The skier starts from rest, so his initial kinetic energy is 0. He does have gravitational potential energy to start with, mgy initial. Well, we want to know, what do we want to know? Speed at the bottom. So he is moving, final kinetic energy is 1/2 mvf squared. I define y equals 0 to be the bottom of the ramp, which means my final gravitational potential energy is 0. There's no air resistance and no friction, which means that there's no thermal energy. So if I look, this big equation reduces down to the following. The work done by this headwind plus the initial gravitational potential energy equals the final kinetic energy. And that's basically our term. We want to solve this for the final speed, but first we need to figure out what is the force done, or what is the work done by this headwind. Now, it's a constant force, which means I can use for work the force dotted into the displacement times the cosine of the angle between the force and the displacement. Couple things. One, what is the displacement over which this force is acting? Well, 50 meters is the height of the ramp, but the headwind is acting the entire time this person is sliding down the ramp. Well, if this is 20 degrees and this height is 50 meters, then you can basically show that, let me do this in a different color, this displacement over which the headwind is acting is the hypotenuse of this triangle, which ends up being, I'm going to call this delta x, is 50 meters divided by the sine of 20 degrees, which ends up being equal to 146 meters. So that's the distance, the displacement over which this headwind is acting. Now here's the big question. Here's one I want to give you 30 seconds to think about. What is the angle that I'm going to use to calculate the work done by this headwind as this person is sliding down the ramp? What do you think? That's the one of the big parts of this problem. So how would I do this is by really just drawing the picture. So let me kind of draw this over here a bit. And again, let me not lose track. This is what we are trying to solve, but I need to figure out what is the work done by this headwind. So one, the person is sliding down this incline. Here's my delta x. The headwind is acting horizontal. Here's my f. Well, this angle here is the same as the angle of the incline, which in this case is going to be 20 degrees. So if this whole thing is 180 degrees, then this angle between the headwind and the displacement is 160 degrees. So you guys can sort of go back and redo that on your own if you need to spend a little bit more time on that. So now I can figure out the work done by this headwind is equal to the force, which was 200 newtons, times the displacement, which was, we found was 146 meters, times the cosine of the angle between the two, which was 160 degrees. So what you end up getting is the work done by this headwind is negative 27,400 joules. In essence, this wind is removing energy from the system. So now what I get is the work done by the headwind plus the initial gravitational potential energy of the skier equals the final kinetic energy of the skier at the very bottom. Let me just skip the step of solving this algebraically. We have work done by the headwind, we have M, we have G, we have Y initial. All we're doing is solving for V final. Which you'll get once you solve this is moving at 16 meters per second at the very lowest point. All right, let me stop this for 1 second. So I think part of the problem with the Zoom not recording is I stopped the lecture and then I restarted another Zoom session to do office hours. And I think there was a slight issue with that. So instead of stopping a Zoom session and then restarting one for office hours, what I'm going to do is just sort of roll office hours right after the lecture. So what I'm going to do is just pause for a minute, see if there's any questions. If not, then I want to do one more example problem and then just do some office hours. So let me just pause. Pretty much I'm done chapter 10. I want to do maybe one more example problem, but you'll see these problems are fairly straightforward once you get used to them. So let me open it up. If you have questions, unmute yourself, throw something in the comment.
That was easy.
Okay, guys, get an easy button. Going once, going twice.
I have a question about that exam.
Yes.
Are we going to be able to get partial credit on the questions?
No, I still have not figured out an easy way. So what I'm going to do is just have more questions, but they will be relatively straightforward. The problems will be 1 or 2 steps. And just so you know, I know that's not ideal. And at the end of the semester, when I go to calculate the grades, I'm going to take into account the fact that this is a completely fucked up semester, excuse my language, but nothing is the same. And so probably rather than doing 90 to 100 as an A, it might be something like 88 to 100 or 87 to 100. People are doing fairly well. And I know that not giving partial credit's not ideal, but I haven't figured out an easy way except for having pictures. People take, anyway, there's no easy way. So the answer is no, there's no partial credit, but the problems will be straightforward and easier, not involving multiple steps. So in essence, we're going to be focusing on just the basics, which is not ideal, again, but I'm trying to do the best I can with this new environment. And I can't give a 10-page exam and have 70 people upload 10-page exams. I can't download 700 pages and grade it. It's just not conceivable.
Do
So,
you recommend that? Oh, sorry.
Go ahead, Carolina.
Recommend that we go over like past celebration number 2?
I'll talk about that. So no, the old quizzes and the old celebrations I have posted were, you know, the old celebrations when I gave it in lab and you had the full 3 hours with just a cheat sheet. So unfortunately, I don't have old quizzes that you can refer to because this is a completely new situation. So again, I'll try and make a video on Friday just talking about how I would go about studying for this. I'll see if I can make up a quick little study guide or something like that. But yeah, it's not going to be the same as it was before. Okay, what I want to do is do one more example problem, and I'll hang out until 12:30 if people have other questions. So let's do one more sample problem. Which should we do? Let's do a great one. This is problem 10.49. And this will sort of be the last example problem I'll do for this chapter, and then we're pretty much completely done chapter 10. A horizontal spring with a spring constant of 100 newtons per meter is compressed 20 centimeters and used to launch a 2.5 kilogram box across a frictionless horizontal surface. After the box travels some distance, the surface becomes rough. Coefficient of kinetic friction of the box on the surface is 0.15. Use work and energy to find how far the box slides along the rough surface before stopping. Okay, I want to pull up a different page for this. So this is problem 10.49. And the situation is I've got a spring connected to a mass. The spring constant is 100 newtons per meter. Then I compress the spring a distance of 20 centimeters from its equilibrium position. Then the spring is released, and this box travels some distance to the right, and then it encounters a rough surface before eventually coming to rest. So here's my spring. Spring is not stretched or compressed, so this would sort of be my equilibrium position. Then I push this mass against the spring, compressing the spring 20 centimeters. So this is going to be my initial condition. And then this spring launches the mass the mass moves across a frictionless surface, and then it encounters a surface that does have friction, and the coefficient of kinetic friction is 0.15. So what we want to know is, what do we want to know? How far this box slides across the surface that does have friction. So we want delta x. We're told that the mass of the box is 2.5 kilograms. The box is compressed a distance of 20 centimeters. Generally, we use negative if something's compressed, so 0.20 meters. Your book, I think, is always using a positive value. It doesn't really matter since for the energy, it's squared. And then what we want to know is, so this is the, maybe I shouldn't use delta x twice. Let's just call this delta r. Delta x is how much the spring is compressed. And what I want to know is how far does this thing move along the surface that has friction? So one question I have for you. Can I do this in one step? Well, let me just say the way most people would do this is, or the way many people do this is, first they would figure out how fast is this spring or is this mass moving after it's no longer connected to the spring. In essence, all of the elastic potential energy of the spring got converted into kinetic energy. But now it's moving across this frictionless surface, and then it comes to this surface that has friction. Because of friction, it eventually stops. All the energy that the moving mass has now been converted into thermal energy. Here's what I want to emphasize. You can do this in one step, where my initial condition is when the spring is compressed. And my final condition is when the mass is at rest. So it's traveled some distance along this friction surface, and because of that, thermal energy was generated. Now, if you wanted to, you could do an intermediate step and figure out how fast is this mass moving right after the spring is no longer stretched or compressed. But the kinetic energy of the moving mass equals the initial potential energy stored in the spring. It's an extra step you don't have to do. So let's be specific here. Let's define my system. And my system, I'm going to define as, what is this? A mass, a box. So I'm going to define as the box, the earth, and the spring. So if I look at the forces acting on the box, I basically have the normal force, gravity mg, and I've got the force of the spring pushing it to the right. Now, once I'm over here, there is a frictional force, but we're going to see, and sorry, I'm also going to define it as the surface. So my system's going to be the box, the earth, the spring, and the surface, which means that every single force is now an internal force. So in terms of external forces, there's none. Right, the normal force is a force the surface is exerting on the box. Gravity is a force the earth is exerting on the box. The spring force is a force the spring is exerting on a box. And once we get to this region with friction, friction is just the resistive force that the surface is exerting on the box. Every force is an internal force. So my big equation is the work done by all external forces plus the initial kinetic energy, plus the initial elastic potential, keep doing EL, plus the initial elastic potential energy, plus the kinetic energy, plus my initial gravitational potential energy, plus my initial elastic potential energy, equals my final kinetic, plus my final gravitational potential, plus my final elastic potential, plus any change in thermal energy. So one thing I didn't do is define where y equals 0 is. And I'm just going to define it as the elevation the box has to begin with. It's not moving up a hill or down a hill. Its elevation is not changing. So given that, I've got 8 different terms. I've got a term for work, a term for all the different kinds of energy. How many of those 8 terms survive? How many of them are non-zero? And the answer is 2. So 1, there are no external forces the way we've defined our system. Every force is an internal force, so the work done by external forces is 0. The object starts from rest and ends at rest. So it starts with no kinetic energy, it ends with no kinetic energy. I defined y equals 0 to be the elevation it's at, so it starts off with no gravitational potential energy, it ends with no gravitational potential energy. At the end, the spring is no longer stretched or compressed, so it doesn't have any elastic potential energy to end with. So what is our big energy equation reduced down to? The initial elastic potential energy stored in the spring all ends up getting converted into thermal energy. So then if I just plug in my equations for each of these, what I have is 1/2 K times delta X initial squared equals the force of kinetic friction times the displacement over which it's acting. And in this case, if you remember, the force of kinetic friction is given by the coefficient of kinetic friction times the normal force. And for a surface, an object that's on a flat surface, there's no acceleration in the y direction and no horizontal forces. The normal force is just going to equal mg. So this is mu k mg for the force of kinetic friction. So what I have is 1/2 K times delta X initial squared equals mu K times mg times delta R. I have K, I have delta X initial, I have mu K, I have M, I have G. All we're doing is basically solving this equation for delta R. And all, you know, all the homework solutions are still posted. Let me just skip the step of writing out the numbers, which you'll get once you solve for delta R is 0.54 meters. So this is a typical energy problem. Again, they're all done the same way. I first, well, there's a lot of information here. Would I go to work energy principle? Not sure what I want to do. Okay, so our big equation is this, that we're pretty much using this entire chapter. So what you do for all energy problems is, in essence, define your system. And that's important because anything outside the system is an external force that could do work on the system. If you want to use gravitational potential energy or elastic potential energy, the earth and spring have to be part of the system. Then all you're doing is, from this equation, figuring out what's 0, what still survives, and then you're just solving for the unknown quantity. And that's really chapter 10 in a nutshell. So let me stop this and open it up to questions. So that's sort of the end of any new material or any kind of stuff I want to present. Now I'm just going to hang out until